Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 4.5, Integration by Substitution. And happy holidays for those of you who are doing this over break. Let's get right into it. All right, today we're talking about using pattern recognition to find the indefinite integral, use a change in variables to find the indefinite integral, use a general power rule for integration to find an indefinite integral, use change of variables to evaluate a definite integral. You've seen a pattern here, I hope, and evaluate the definite integral involving an even or an odd function, which is kind of a um, minor thing that you can use in calculus. But anyway, here we go. The antiderivative of a composite function. Let g be a function whose range is an interval I, and let f be a function that is continuous on that interval I. If g is differentiable on its domain and f is the antiderivative of little f on I, then the integral of f composed with g times the derivative of g is just capital F of g of x plus some constant c. In other words, if you have a function that's defined in f, you can do a substitution with u, and this is just the g of x, and then the du is the g prime of x dx, and then f of u plus c. And let's talk about what that actually means. So let's kind of talk about it in terms of what we already know versus what we're learning. Okay, when you do the derivative of a composite function, remember it was the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. That is the chain rule. And so when we do the derivative of this thing right here, and I say f prime of x, I am going to take the derivative of the outer function, which is just the x to the fourth. That'll give me 4 times x squared plus 2 now to the third times the derivative of what's inside, which is just 2x, and then the derivative of the plus 9 is 0, because the derivative of a constant is 0. So you'll notice here that we have this additional multiplied term for the derivative of that inside function. So when we go to do the integral of this function has to disappear. So when you think of this setup here in terms of that integral that we're trying to find, we look at it like this. So when I say, well, let's look at it here. This portion right here, that's my g of x. This portion right here is my g prime of x that I'm looking for. So there's that additional multiplied term that we're looking for. All right. So let's go and do just a real quick example and show you how we can do the full u substitution. So in this context for this particular problem here, and again, I'm going to be using kind of this notation right here. What we want to do is we want to say, all right, let's let the inner function of some part be u. So we're going to let u in this case be the inside of this x to the third function. And so we're just going to say it's x squared minus 9. And then what we're going to look for is the derivative of this. So I'm going to say du is going to equal, well, what's the derivative of this? Well, it's 2x, and then remember it's du over dx, so we'll just use the marginals or the differentials that we used in the last section for derivatives and call this 2dx. Now, we want to do our substitution here. Notice this part right here is my du. This part right here is my u. So I can do this substitution and say that this is u to the third du. And now that everything is in terms of u, I can just do the simple power rule on this. And do the integration of this thing and say it is 1/4 u to the third, excuse me, don't screw it up, still 1/4, u to the 4th plus some constant c, and then substitute back in for x. And that will give me 1/4, and then it was x squared minus 9 to the 4th plus some constant c. This is our final answer for this integral. And you can see very easily that if I do the derivative of this thing, I bring the 4 down, 4 times 1/4 cancels, and then it'll be to the third, and then it'll be, not 2, it would be x squared minus 9 to the third times 2x, which is what I have up there. So basically what we're looking for is we're going to try and find some inner function that we're going to call u, and then what we're going to try and do is take the derivative of that thing and find that extra part, that extra chain that had to be eliminated in the integration process. All right, so let's look at this one and see how we might redo that one. So I look at this, and again, I look for the most complex part that's kind of in an inner portion, and I see this x, or 1 plus x to the 4th. So I'm going to let that be my u. I'm going to go u equals 1 plus x to the 4th, and take the derivative of that, dx, or excuse me, du is going to be equal to, well, the derivative of 1 is just 0. The derivative of x to the 4th is 4x to the 3rd, and then dx, just to keep my differentials together. So this is what I'm looking for to try and replace. This is the portion that is going to disappear from that kind of reverse chain rule. So I see I have an x to the 3rd dx, but I don't have that 4. Well, that's okay because it's just a constant. So I can put that constant out front and go 1/4. We'll do the integral, and then we'll rewrite this. We'll say that this is 1 plus x to the 4th to the negative 1/2, and then we'll put that extra 4, x to the 3rd dx. Now, 4 times 1/4 is 1, so I am not changing this function. And now I can replace this portion with du, I can replace this portion here with u, and say that this is 1/4 integral u to the negative 1/2 du. And now I can do the simple power rule. Very easily here. And all right, so I'll have 1/4, and then this will be u to the 1/2 over 1/2, and then plus some constant c. If I divide by half, it's like multiplying by the reciprocal, so I'll be multiplying by 2. 2 times a 4th is a half, so I have a half u to the 1/2 plus c. Replace or substitute back in K. McCulley in for x, and we'll have this, and then it'll be 1 plus x to the 4th to the positive 1/2 plus c. And again, if you do the integration of this, you will most certainly get this back. Or I'm sorry, take the derivative of this thing, you'll get the original integrand back. Okay, so let's talk about changing of variables. Now, when I say change of variables, I look at this particular problem right here, and I notice that I have a function under a radical, and I have an x. So everything's defined in x. And the problem with this is that I cannot distribute this x to these two terms because of the exponent. You can't distribute across exponents. That's not possible. But what I can do is I can change the variables so that this thing is just a u to the 1/2, and then I can replace this x with something else. So let's check this out. If I solve this function here for x, solve it by itself, well, I have to add 1 and divide by 2. So I can say that x is equal to u plus 1 all over 2. Well, let's do the derivative of both of these. Well, the derivative of u with respect to x is just going to be 2. And then dx. And then dx will be just 1/2 du. All right, well, that looks good. So what good does this do me? Well, notice what happens here. Now I can replace this thing with just u, and so rewriting my integral, I have u to the 1/2. That's what this is right here. And then I can replace x with, let's rewrite it as 1/2 u plus 1/2. Yeah, I like that. All right. Now I have to change my x to u. Well, um, uh, I need 2 dx to change it to du. That's okay, because it's just a constant. I need 2, well, let's redo it here. I need 2 dx, so I'm going to have to get that 2 dx there. I'm going to need that half out front, and now I can replace it with just du, because then 2 dx, 2 times 1/2 gives me that 1. All right, so now how does this help me? Well, I couldn't distribute the x across the parentheses with the exponent, but I can distribute this u to the 1/2 across this thing because there is no exponent there. So I can say it's a 1/2 integral 1/2 u to the 1 plus a 1/2 would be 3/2 plus 1/2 times u to the 1/2 now du. So now I can do this thing, and I can do the simple power rule on both of these two terms. If I wanted to bring the half out, I probably could, but I'm not going to worry about that just yet. So I'm going to go 1/2 times, well, let's see here. It'll be 1/2 u to the 5/2 all over 5/2. That's a multiplication, plus 1/2 u to the 3/2 all over 3/2, and that's going to all be plus some constant c. All right, so let's see here. If I flip this one and multiply, so a 1/2 times 2/5 is going to, I'm going to still have that half out front, but it'll now be 1/5 u to the 5/2 plus, now if I flip this and multiply, the 2's will cancel. I'll get 1/3 u to the 3/2 plus some constant c. And then finally, let's just distribute this half and make it 1/10. And you know what? Not only let's do that, but let's resubstitute in for x. And it'll be, because remember x was, or u was 2x minus 1. So I'll have 2x minus 1 to the 5/2 plus, and again, I got to distribute that half. So I'll have 1/6 times 2x minus 1 to the 3/2, all plus some constant c. Now, when you take the derivative of this thing, it isn't going to come directly out to be our original integrand, but we certainly could manipulate it down to get that. All right, so just in general, some guidelines for making change to variables. Choose a substitution u for g of x. It's usually best to choose the inner part of a composition of functions, such as a quantity raised to a power. And if you remember from our last one, we are raising this quantity 2x minus 1 to a power. It's just a 1/2 power. Compute what du is, and du is just going to be g prime of x times dx. Rewrite the integral in terms of the variable u. Find the resulting integral in terms of u, and then replace u with g of x to obtain the antiderivative in terms of x, and then check your answer by differentiating. For definite integrals, though, and we're going to do one here as my last example, we can skip steps 5 and 6. By finding a new upper and lower bound with your equation for u. So let's take another look at the one that we just did here. So this one here, we have the integral from 1 to 2 of what we had before. And so we're essentially going to do the same thing. We're going to say, all right, let's let x be equal to u plus 1 all over 2, which was, again, 1/2 u plus a 1/2, and then du is going to equal 2 dx, and then dx will be equal to a 1/2 du. All right, so let's do our substitution. And again, we have our integrand here, and it's back to what we had before. So it's a half of u plus 1/2. That's not a very good half. Let's see if we can do better. And then u to the 1/2 power dx. But again, this is a definite integral. So we have to, what we can do, instead of doing these bunch of extra steps here at the end, after I've done the integration, I can change my upper and lower limit by replacing them with upper lower limit in terms of u. And I made a mistake here. I have to change that to du, so I need my half out front. And this, we did this on the last one, so I just want to make sure that I have them all straight. So all I have to do is change my upper and lower bounds, and that's simple. We just plug in. We go 2 times 1 minus 1 is 1. That's my new lower bound. And so a 1. And then go 2 times 2 minus 1 is 3. That's my new upper bound. And so we'll just replace those. And since I did the integration in the last one, we're just going to use this thing right here. And since it's a definite integral, I don't need the c. So I'm just going to replace it. It was a half, 1/2 integral 1/5 u to the 5/2, and then it was plus, I think it was 1/3 u to the 3/2. And now, instead of replacing and doing all those extra steps, since I have my new upper and lower bound, I can just evaluate it from 1 to 3. And we'll distribute the half and plug in. So it'll be 1/10, and then it'll be 3 to the 5/2 plus 1/6. Again, I'm distributing the half, and then it'll be 3 to the 3/2, and then minus, we'll have 1/10, 1 to the 5/2, plus 1/6, 1 to the 3/2, and then we just need to evaluate that thing. Oh, let's see. Well, these are easy. It's minus 1/10 plus 1/6. And I'm going to pause and do the calculation here, and I'll be right back. So let's pause. Okay, I'm back. Neither of these turn out to be rational numbers, which I should have seen. Anyway, so I guess at the end of the day, this ends up being 3 to the 5. Oh, shoot. I'm not tight. Oh, crud. Doesn't want to write. Okay, well, anyway, this ends up being 3 to the 5/2 over 10 plus 1/6 to the 3/2, or 3 to the 3/2 over 6. And this turns out to be 4/15 when you find a common multiple and simplify. And so the whole thing turns out to be, let's see here, the whole thing ends up to be 2.158. And I don't know why it's not typing for me. Let's see if I can't fix something. Maybe go to draw, go back to select, get my select back on, see if that works, see if that helps me. I'm not being able to select anything. It's kind of ticking me off. But let's see here. Okay, so we'll just write on this one. So the final answer for that last one ends up being 2.158 is the integral after you've evaluated it, because again, it comes out to be irrational numbers. All right, folks. Well, that's all I got for today. If you have any questions, feel free to give me an email. Thank you, and have a good break. Bye.